So this is again one of those super long, well, I mean they're all super long questions, but this one is related to Maxwell's equations. So first part says write the general frequency domain Maxwell's equations in the point form. Now we've done this before, but we'll do it again because it's good practice. So we have tutorial 3. So part 1 or question 1A says write ME, abbreviating Maxwell's equations, in frequency. Okay, I mean this is, everyone should be able to do this by now, I should hope. But we'll do it anyways, just because when he starts in lecture, he usually starts from here. And I guess if you can do this, it's definitely worth marks. So, you know, we need all the marks we can get. This is Amperes Law. This here is Gauss's Law. And this here is, well, not really Gauss's Law, but they call it Gauss's Law for magnetic fields. So that's part A. Write Maxwell's equations in the frequency domain. So that's literally one question. And that thing itself, that right there is worth 8 marks. So on average 2 marks per equation. Now the next part, I don't think we've seen this before. We've discussed it briefly before, but we haven't seen it. It says write briefly about all possible current densities and include, whenever possible, the relevant equations that define these current densities. So you know we have different types of currents. We have impressed current, conduction current, convection current, and displacement current. So it wants us to first list what types of current we have. So it wants us to list those 4. Then it wants us to, wherever it's possible, to write the equation for those currents. So what we're going to do is, we literally just list them off. So we'll have impressed current. Now, the thing about impressed current is there's no equation for it. So for this, we're just going to write Ji, and we're going to say it's a function of space and it's a function of time. And that's it. That's how we define impressed current. Next we have, yes?
Is that the one where you write the I on top?
Right at the top, right at the bottom, wherever you want. It's the same current though.
Oh.
So you can write it at the top. You can write, I like writing at the bottom just because it makes more sense. Right at the bottom. I like subscripts better than superscripts. That's me. If you want to write it at the top, write it at the top. More power to you. Conduction current is, we're going to call J cond for conduction. And this is a function of, again, space and time. Make sure you include this because it is relevant. And the equation for this is sigma E. And now, it doesn't say whether it wants it in frequency or in time. So we're just going to assume it wants it in time, okay? So this is just E. There's no ES there. So again, electric field is a function of space and time. So we write that there. Then we have here the convection current. Now does anybody know how we define convection current? Convection, this. Rho VU, rho subscript VU, yes, you're right. So that's essentially due to speed, or the movement of charge. So rho V is the charge, and then we call U the speed. So U is a function of space and time, and U again is also a vector, because it's a velocity basically. And finally we have the last current, we have displacement current, which I guess everybody should know, because this is the one thing that changes in Maxwell's equations from when we initially see them to the end. So we'll call this J subscript B as a function of space and time is equal to the partial derivative with respect to time of the electric flux or displacement field, wherever you want to call it. Let me make that a square bracket so I can put this on here and that doesn't look too bad. Okay. That's part B. Any questions about that? That's literally what it wants. It wants you to list all the types of currents and define them where possible with an equation. Again, 8 marks right there. So, simple marks. For things that I guess we should all know. Now, the next question says, I guess I should probably write along as I'm going here, because these will be notes after. What the question asks. List all types of current. I'll make that a different color too. I'll do that starting from now on. Okay. So that's that. So now part C says, let's use green, says use Maxwell's equations, and we're going to define the frequency domain vector potential. Now, for those of you that don't know, the vector potential is that field that we call A. Now, I'm positive he derived it in class, and I'm also positive nobody understood it. So we're going to go, and this is, since it's a question, we're going to have to answer it. So we take this Gauss's law for magnetic fields, which we know to be true. Now the thing here is, there's actually a vector identity, and I'll write the vector identity here. Vector identity that says if I take the divergence of the curl of some field C is any field. I'm not using A or B because we have fields called A and B and I don't want to confuse it. So if I have the divergence of the curl of some field, this equals 0. Now, what the vector potential is essentially it's a mathematical manipulation. So what we say with the vector potential is we say, well, vector potential is A, so we'll say vector potential is AS, we'll say in frequency. But now, we have to relate AS to B is essentially what the purpose of having a vector potential is, because in certain cases it's easier to find the vector potential than it is to find B directly. So what we do is we find the vector potential and then we can go to B from that vector potential. So essentially the way these are related is if I take this and I define, let's say, the curl of AS, so this is the relationship between B and A. So you see we take the curl of A to get to B. And now the thing is, again, it's a mathematical manipulation. So you can see that this identity here is what lets us do this. So this, physically speaking, the vector potential, if I talk about it physically, it doesn't exist as a physical thing. It's entirely man-made. The magnetic field and all these kind of things we can measure, these are things, but this vector potential is, we create it to compute the magnetic flux density B a little easier. So essentially what this question is asking is, how do we define, what's the relationship between BS and AS? And so given these two things, we realize that BS must equal the curl of AS. And let's use purple for our final answer, because I think that's what I did in all the other videos. Okay, that's part C. Now, this next part, he also does in class, and this is also in your textbook, so if this part doesn't make sense where I do it, maybe you can go back to your textbook and look at it there. I think their derivation is a little more tedious, but essentially it says, again, we want to use Maxwell's equations to derive an expression for ES in terms of V and AS. So those are the scalar and the vector potential. So the vector potential we just defined here, and now the scalar potential is just V, where you have, you probably remember from field theory, right to the side here. Recall, I'm sure you all remember this, and at this point you probably all thought this course was going to be so easy, because we just take gradients and you can compute fields. And joke's on you. So, we have this case, we have this thing here. Now what we want to do is we want to express entirely ES entirely in terms of V and AS. So here again we have some mathematical manipulation we have to do, but we start with Maxwell's equation. In particular, we start with Faraday's law, and we want to be in the frequency domain. So this is minus j omega bs. Now, I guess I can also write here that bs equals the curl of as. And so what we're going to do is we're going to substitute bs into this equation here. So the curl of es is going to be minus j omega the curl of as. Okay. Now what I'm going to do is I'm going to take the minus j omega and I'm going to move it inside, because j omega doesn't depend on space, so we can actually move those things around. They're constants. So I can say that the curl of es is equal to the curl of minus j omega as. Okay? Now if I move this entire thing to the left side, I get the curl of es minus, well, I guess I can take that minus outside and that actually ends up becoming plus. So what I'll get is plus the curl of j omega as, and this whole thing is 0. Now I can factor out the curl, and essentially what I'll get is the curl of es plus j omega as equals, equals 0. So here we have the electric field related to the vector potential. Now we need to relate it to the scalar potential and then get the entire equation as one big thing. Now that part requires knowledge of another vector identity. So I'll write vector identity. And so essentially what this vector identity says is that if I take the curl of the divergence of some field, this equals 0. Okay? Now, what we do here then is we take, if the curl of this gradient v, or negative gradient v, equals 0, I have here two equations that equal 0. Now logically speaking, that means I can equate these two equations. Typically it doesn't mean anything. If I have two equations that equal 0, I set them equal to each other. We can do that, that's no problem, because both things equal 0 at the end of the day. In most cases that's called a trivial solution because they equal 0, but in cases like this we find that we can actually relate certain parameters. So now since this one equals 0 and this one equals 0, I can set both of these equations equal to each other. So I'm going to say equate, sorry, one sec. There? Better? So if I equate 1 and 2, then I get that the curl of es plus j omega as is equal to the curl of minus the gradient of v. This should be curl. And so now if the curls are equal, that means the two things inside the curls must also be equal. And then so I get that es plus j omega as equals minus the gradient of v. And so finally I get that es equals minus gradient of v minus j omega as. Vector signs missing. Okay. And that is our final expression. Have you guys seen this expression before? No? I'm sure, if you're in Ali Hussein's class, I'm sure you've seen it. I'm positive you've seen it because I know he does it. Because I hadn't seen it before he did it either. It's in the textbook though, I promise you. It's pretty much what we have to do is we take into account, initially when we define E in terms of this, just the gradient here, when we do that in field theory, we're not accounting for a time varying component, meaning we're not accounting for the fact that electric field and magnetic field are coupled. Now that we know that the two fields are coupled, we have to account for both of them. And so this j omega actually, if you were to consider it in time domain, is a time derivative. And so what that means is that the fields are related, which we know after we understand the idea of an electromagnetic wave. Initially they're lying to us and they're just telling us that E is just the gradient of V. In reality we know it's not. They might be, they might not be, but they're simple. I mean, if it's the derivation you should know, then I guess you should know the identity as well. You know, I mean, I don't know what he's going to give you, what he's not going to give you, because I've seen certain cases where he gives students a lot of things, and certain cases he doesn't give them anything. So I guess it depends how he feels. So this next question, I think, is probably the most involved of the entire first problem. So this is part E. Any questions so far? No? Part E. This is we're expressing the electric field in terms of the scalar and vector potentials. Okay? Right, because remember before we used to define it just in terms of scalar potential. Now we have the vector potential to account for as well. Okay, so now what we have is we want to derive the frequency domain. Now everyone's going to sit here and look at me like, what the hell is this guy talking about? This vector equation. Like, we don't even know what this equation is. It's probably what most people are thinking. For the vector potential. And I'm sure he's done this in class as well. Most people probably fell asleep doing it. And state the frequency domain Lorentz condition. Now I'm just talking about something completely else. Lorentz condition. So we want assume linear isotropic, I'm just going to write iso, and homogeneous, not homosexual. For some reason that's funny, I don't know. Loss-free region. Now, does anybody have any idea what this is asking us to find? You can't just tell me what I wrote back to me. Okay. Right. You did this one. Okay, then you're cheating. It doesn't count then. Well, no, it's good that you know what to do. That's good. That's the purpose of being here. So we should learn what to do. Sorry? Yes. Yeah. So yeah, he's right. We take Amperes Law. We take the equation for the vector potential that we just defined. So we have B equals curl of A. Then we take the equation for the electric field that we just defined. So E equals minus gradient V minus j omega A. So we take pretty much all the equations we just derived, we put them into Amperes Law, and then we have to solve and get some equation. Is essentially what this procedure for this question is. Again, this derivation is also in the textbook. It can also be done for the vector potential. So in this case, we're going to have an equation entirely in terms of A and Js. You can have it in terms of V and Js, I believe. But don't quote me on that. So, I mean, it's in your textbook. Chapter 9? Yeah, somewhere in chapter 9. Sorry? Well, I mean, it depends on how you define it. You can use rho V, you can use J, whatever you want. But we're going to use Js here because we want to consider general current. So, we start with Amperes Law, as our friend suggested. Js plus j omega ds, and it says in the frequency domain, so everything is in the frequency domain here. So I'm also going to write here on the side, recall that es is minus gradient of v minus j omega as. What else do we have? We have bs is equal to the curl of as. Then we have also, we might need to use that bs equals mu hs, but I guess this one you should all know off the top of your head at this point. So what I'm going to do is I'm going to first get this expression entirely in terms of h and e. I'm going to leave j as it is because I don't know what j consists of, so I'm just going to leave j as it is for now, and then we'll define it in terms of whatever it is later on. After reasoning with whatever we need to do. So right now we're going to leave j as it is. So what I need to do is essentially substitute epsilon e into ds. So I leave Js as it is. I get J omega, I get epsilon, and I get Es. I'm leaving epsilon as epsilon. I'm not calling it epsilon, not saying anything else. It does tell us that it's isotropic, whatever, blah, 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 but it doesn't tell us it's dielectric, so we don't know necessarily what it is. So now what do we want? We want to be able to substitute all of these equations in at one point or another. So these equations here, we are going to use all of them at one point or another. And so I guess right off the bat we can use this one. And so we can say that the curl of Bs over mu is Js plus J omega epsilon Es. Okay. And now what I can do is, vector sign. So I can multiply the mu up now, so I get the curl of B S is going to be mu Js plus J omega mu epsilon Es. Everybody with me so far? Now what I'm going to do is I'm going to substitute Bs equals curl of A in. So I get this curl of this curl of As equals mu Js plus J omega, sorry, forgot the mu epsilon Es. Okay, now what I'm going to do is finally I'm going to plug this one in. So I'm going to put that into Es. So we get this curl of As equals mu Js. So it's close. Plus J omega mu epsilon. Now this thing is minus the gradient of V minus J omega As. So now I have everything. I have a bunch of A's, I have a J, and I have a V. So now where do we go from here? Now there's also an identity. I know a lot of identities, right? So vector identity. If I have the curl of this curl of C, it equals minus this, we call Laplacian. He puts the dot in the middle to signify that it's a vector gradient, plus what? This divergence, no, gradient of the divergence, right? I believe, yes, gradient of the divergence. C. So this is a vector identity from, you would have learned in math 312, I believe. Not that anybody remembers. So let's go ahead and rewrite this curl of the curl on the left side using this identity. So I get minus this curl, this Laplacian, we call it, plus this gradient of this divergence. Now this whole thing equals mu Js. So how do I want to do this? Let's say minus this divergence. No, let's do this. Okay. Let's say minus J omega mu epsilon gradient V and minus J squared omega squared. About 2. That's better. Mu epsilon As. Right? Right. So now I have a whole bunch of things here, and I don't know what the hell's going on anymore because I'm so far in that everything stops making sense. So now at this point it's just a mathematical sort of manipulation. It asks us, if you remember at the beginning we said here, this thing, this part, right? Does anybody know what the Lorentz condition is? No, didn't expect it. Sorry? You essentially, you make this equation easy for yourself. So we define something that we don't know as something that we don't want to be there, and so we get rid of it. I'll show you what I mean. So what I'm going to do first is I'm just going to write this. So I get this here, and I get, still, this is all just rewriting it. So So what I'm going to do is I'm going to pull this gradient outside, and I can do that because all of these things inside are constants. So the j omega mu epsilon is a constant. Whether I pull it outside or inside, it's the same thing. Mu epsilon as. Now if you look at this entire expression, if you just compare this term with this term, they both have a gradient. And they both have a thing inside. Now the thing is, we don't know this. I don't know about you guys, but I don't know what this is defined as. Divergence of A? I have no idea what it is. We don't have an expression for it, because that's what the Lorentz condition is. So what we say is, this Lorentz condition we say, let the divergence of AS equal minus j omega mu epsilon v. So you see, I'm literally just forcing the equation to do what I want it to do. And we do this a lot in math. This thing right here, this thing I'm defining, the divergence of AS is minus j omega mu epsilon. That's actually an equation. I'm not just making it up, but that's how we get to that result. They just make it up. This is because he shows you in lecture. This is, I mean, it's understood if you've learned the topic, but I mean, when you think about, let's say historically speaking, it's an arbitrary choice. You can do whatever the hell you want, but does it actually get you where you want to get to? That's the question. Exactly. Does the condition help you get anywhere? Because this is going to help me get somewhere. Because that's the Lorentz condition. Why? You literally, you literally just pull it out of the air. You pull it out of the air. I swear to God, you go look at the textbook. It says the exact same thing. This is the Lorentz condition. The guy who was solving the equation, the guy who was defining it. Exactly. Look, I have this sort of symmetry that's defined as this, and you go ahead and you do that. I'm sorry? The thing is, look, there is no expression for the divergence of AS. This is the expression for the divergence of AS. Why? Because it works in the equation. I know, it's very arbitrary, and it's like, where are we even doing science anymore? Where does the math even, like, this isn't even math anymore, this is just guessing. I know, I totally get that, but that is the Lorentz condition. And so now you see, if I do that, and if I apply this, Lorentz condition, then I get this minus gradient. Well, I'll take the minus inside now, because the minus is inside on the other side. I don't know how he figured it out. Apparently nothing else to do, yeah. So then you get this thing cancels with this thing, and now all of a sudden we're left with... See, the thing is, in science, a lot of the time, pure, like hard science they call it, a lot of the time you know certain things that should be true, and you just kind of force them to become true over time. I mean, in engineering we don't do that because we guess and then we work towards it. But in science, like they knew this equation should take on this form. So then you can start building off of what you know and get new sort of conclusions for that thing. That's just the way science works. So I get this minus, I'll bring this plus j squared omega squared mu epsilon as here, and this will be mu js. And now what do? I'm just going to divide. I'm going to get rid of that negative sign. So I should get this as. J squared is just minus 1. So omega squared as equals mu js. And if you remember what our wave equation looks like, this looks awfully similar. But not exactly the same. So this is what we call the vector Poisson's equation. I'm sure there's a reason as to why you can pick that condition and why he picked it when he derives it initially. Whenever he did, I think it was sometime in the 1800s. But for us, just know what it is. Don't care about where it came from. He also wants us to, there is marks for writing that Js equals JSI, so the impressed current. Let's keep it consistent right at the bottom. I plus rho VSU. And to note that sigma E S equals 0. This is because it's loss free. And if it's loss free, that means the conductivity is 0. And if the conductivity is 0, then there's no conduction current. So it tells us here it's loss free. Right there. If it's lossy, it should give you something. It should give you something. How is it lossy? It'll give you some sort of attenuation coefficient. And we'll see that in the next problem? No. In the last problem, we'll see that. Which part? Good? It's good? So that's the entire first question, and that entire first question is worth some marks. Where did I put it? 40 marks. I'm sorry? How many marks? Yeah, you pretty much passed the test if you got this entire question in. The whole thing, beginning to end. The beginning to end, the whole thing. Everything we've done so far is worth 40 marks. This last part we did is worth 14. Yes? There should be, you're right. Oh, there's a quarter mark lost right there, guys. Don't forget your vector signs. I'm allowed to. I literally just divided it. Multiply the equation by -1. Multiply the equation. Oh, sorry, this should be negative u mu. Well, the omega changes because j squared is -1. I think you're right. Minus, plus, -1. You're right. Plus. I believe. Yes, you're totally right. You're totally right. Sorry about that. From this step here, I multiplied the whole thing by -1. So I get minus j squared. J squared is -1, and then negative that. So is that cool? Like, I mean, questions like this, how do you know this? You don't know it off the top of your head. You have to learn these derivations, which I think are silly questions to ask, just because it just tests how well you know the derivation and not how well you actually know anything. But they are asked. They are asked questions, and they appear more than once. As you saw in the last one, we derived something. I think we derived the wave equation in the last one. So they do appear, these questions. Right. What I'll do with that one is maybe I'll make a video separately and post that one separately, because just in the interest of time, because these things are they're time consuming and there's not much there to learn. It's just a derivation. But I will do that. Hopefully tonight or tomorrow. Okay, this next question is fun. This is one of those retarded potential ones. No, literally, it's called retarded potential. I don't know why that's funny. It could be. I don't know. The thing is, if you know what the end result looks like, you can kind of bullshit your way through the entire question. Like, even if you don't know where you're going wrong in certain steps, if you know what the final end result looks like, you can kind of say, like, even if you don't know that the divergence of A is equal to that thing, you look at your equation and say, this is what it should look like. I shouldn't have this term. Therefore, it should equal this. So you should be able to, I mean, I hope you guys can reason like that. Then again, I don't know. So here it says we have a surface charge. I'll write this in green because I've been doing that the entire time. Surface charge rho s in free space on the surface defined by this is A, so R between A and B, theta equals beta, beta is less than pi over 3, and phi is between 0 and 2 pi. It should be 0, phi, 2. Okay, so this is one of those field theory type questions, but it's with it's taking the fact that it's a traveling wave and that it will take some time for the thing to propagate into consideration. I think a question like this will be most likely will be on your test because you haven't covered transmission lines. In the cases where transmission lines were covered, these kind of questions don't usually appear. I'm just speaking from, I guess, experience. This is my first time TAing the course, so I don't know. I'm just speaking from experience and what I've heard from other people. So the first part asks you, sketch the configuration. And I kid you not, this is worth 4 marks. Just sketch. So we are going to go ahead and sketch. There we go. Okay. So we have X, Y, Z. Yeah, it's kind of unnecessary, isn't it? I think we should extend that a little further. Are you calling me a show-off? No, that's totally showing off. That's totally just using it because you can. I know. I agree with you. That's the purpose. Okay, so it says you have. That's the first thing we should do is it says beta equals beta, and beta is less than pi over 3. If you remember how theta is defined, it's defined as the angle between the z-axis. So essentially, what we're going to have is if this is right on the z-axis, pi over 3 is going to be something like this. So it's going to be in that top little bit. So what I'm going to do is first I'm going to just extend a line here like that, and so this is going to be our theta equals beta line. Then it gives us that R is between A and B, so R is somewhere between here. We'll call this R equals A, R equals B. And then it gives us that phi is between 0 and 2 pi, so you know it's going to be this sort of, I guess, ice cream cone without the bottom. So when you bite off the bottom of the ice cream cone, it's going to look like that. So I guess we can just draw a little thing like this, like that, and so this part will be round here. This is solid, and we're going to assume this thing looks something like this, and of course this is 3-dimension, but it's difficult to draw this in 3-dimension. So this is something like this. Okay, so it's this sort of dome ice cream cone. I mean, it would be an ice cream cone if it was like down like this. That's not. So it's just that bottom part's missing. So imagine a cone with a round top, and now chop off the bottom of it, the pointy part of it. So that's our sketch, and that's worth 4 marks right there. That you know what it looks like. Does that make sense to everybody? Part B, it says find the scalar potential at the origin given. So it gives us this expression for V. Yes. Yes.
I know that R is not from the center to the point.
You don't. It can be anything. I'm just assuming it's something arbitrary. You can put whatever you want. You can make it bigger. You can make it smaller. You can put it right to the origin. But the thing is, chances are, if it's given you an R is not 0. Well, if it says R is between.
I know the top circle.
Yes.
outside, you know that R is not over there.
It could be. It makes no difference, really.
Oh.
Because at the end of the day, when I integrate it, it's going to take care of everything. This is just me assuming this is probably the simplest thing. You could probably say that B is the top of the ball, the dome. Like, you can probably say that this point right here is B. But at the end of the day, it makes no difference, because when I integrate it, it's going to get taken care of anyway. This is just a sort of rough sketch so we understand. Like, the specific details in this case don't really matter. You should have a sort of general... The most important thing to realize is that it's in this quadrant, first of all, that this angle is less than pi over 3. So it's less than 90 degrees. It could be anywhere. I mean, even if I drew it out like this, it wouldn't make a difference. Because at the end of the day, it's less than that. We don't care about the exact thing. And then again, R between there, it should be any 2 points. Sure, you can put it at the top of the unit. It makes no difference. Because at the end of the day, the equation doesn't care. The equation just shows you an expression. And so even with this drawing, sure, it's a good sort of approximation. It's a good way to look at it. But you shouldn't take it for, this is the only way it can look. Okay. So I have here, this is the equation. This equation is given, by the way, in the question. Okay. And now it says to use or to show all of the, it says show all steps in derivation. So pretty much that means show all your vectors. Show how you get R, show how you get R prime, show how you get R minus R prime, then show how you get the magnitude, and then show how you get ds, and show everything. Just, you want to see the entire sort of thing. So we start, let's say, what we call the field vector, which is the point that we are computing the field at. This vector we define as R, and it's 0, because we said we want to find it at the origin. That's what's given in the question. Then it says, find the source vector. Anybody tell me what the source vector is? No, it's not 0. Why did I write 0? R. Exactly. So essentially you just want a vector that goes from the origin to the source. Now the thing is, we pick RAR because that's the thing that's varying, and we can and any other sort of well, the direction of the vector is really, if you have a three-dimensional thing like this, the way we define this is x, y, z. AR, well, AR is in the direction away from the origin. Theta is sort of along this type of direction, and then your A phi is sort of in this, what they call the azimuth angle sometimes. So it's in this kind of a direction. So this is A phi. So I mean, this is from, again, Math 312, simple stuff. So we know that that's RAR. Now it asks, well, it doesn't ask, but we have to find R minus R prime, which is simple, just minus, we'll call this R prime because typically when we use our thing, we call the source, anything that has to do with the source, we usually define with a prime. So let's use a prime, AR. So then that means that the magnitude of R minus R prime is just going to be R prime. Now ds, how do we define ds, or ds prime as you call it? How would I define ds for that? So the thing to look at is usually what's constant and what's varying. We know that theta is a constant, so we know we're not going to be integrating theta. So you will not have a d theta. So what changes? We have phi, so we have to have a d phi. And we have r is changing, we have to have a dr. Now the thing to consider is how do they work in spherical coordinates. Do you have a question? Square root of r squared. Right? That's how we define the magnitude. So the thing that's changing is r, so we're going to have a dr in there somewhere, and phi is changing, so we have a d phi in there somewhere. Now, if you recall, whenever we have certain components in certain coordinate systems, we have these sort of things that we have to multiply on. So for example, if I'm saying dr, I can just say dr directly. Dr is no problem. So dr is going to take care of my change in radius. Yes? Rho s, sorry, rho s is given. It's given, it's totally given, sorry. Okay. Rho s is rho naught cos theta sine omega t. You're totally right, sorry about that. And it says that rho naught is positive and real. Thank you. I would have needed to add that in there later, but I would have caught on, but thanks a lot. And we're also going to need to take into account that time retarded version of it. So we have dr prime. Now we have to account for the d phi. And now whenever we have a d phi, we say, exactly, r, we're going to say r prime because we're calling everything that has to do with the thing prime, sine prime d phi. Does it make a difference if I write prime or not? No, it doesn't. But it's just a convention. And it's good to follow the convention. So this is what my ds is going to look like. Now if I make it look a little, oh, this is phi prime as well. If I make it look a little, you know, more like what I'm going to use when I integrate it, it's going to be prime, dr prime, d phi prime. So now I have this thing that's going to vary with r and it's going to vary with phi. Okay. Now we have to do the last thing is we have this rho s, and these little square brackets mean that it has the time retardation on it. And so this is going to be rho naught, what did I say it was? Cos theta sine omega t. Cos theta sine omega t. We're actually going to replace t with t prime, because t prime is that takes into account that it's the time retardation. And we're also going to substitute theta equals beta, because we know that to be true, right? So we have rho naught is cos beta. Let's deal with that first. And then we have this t prime. Does anybody know how we define t prime or take into account that time retardation? Exactly. Well, we call it, we usually use a capital R to define that r minus r prime. So exactly. So we have t equals t minus r prime, which is just exactly. So it's going to be this thing here, right? So it's going to be r prime over c in this case, because I believe we're in free space. Yes, free space. So t prime is going to be that. So we have that rho s is rho naught cos beta sine omega t minus r prime over c. Then your c is different. It's not c. It's u, which is equal to 1 over mu square root. 1 over square root mu epsilon. Right? In this case, it's mu not epsilon not, so it ends up being c. But in the case that it's 1 over, let's write that here. If not free space, u does not equal c. U equals 1 over square root mu epsilon. Right? I should hope so. So now we can plug everything into the integral and start integrating, which I guess is probably relatively simple. V S is going to be rho naught cos beta sine omega t minus r prime over c divided by 4 pi epsilon naught. R minus r prime magnitude is just r prime, we said, right here. And then I'm going to have this times r prime sine theta, we said, correct? This thing here. But theta we know is just beta, so I'm going to plug that in there as well. Sine beta. Then we have dr prime d phi prime. Okay? I guess I should put my, well, no, I'll do it in the next step then. So what I'm going to do is I'm going to pull everything that's constant out. I guess we can cross these, cancel these things as well. So I'm going to pull all the constant terms out. Cos beta sine beta over 4 pi epsilon naught. Phi equals 0 to 2 pi d phi prime. And then what else do we have? R, right? R equals A to R equals B. Sine omega t minus R prime over C. I should hope. dr. I guess these should be primes as well. Any questions so far? So this is a relatively simple integral. It's literally just a substitution. So you would substitute u equals t minus r prime over c, do the integration, whatever. So I'm not going to go through all that nonsense. I guess you guys can, you can figure that out on your own, I would hope, at this point. And then this integral here is even easier. It's just multiplying by 2 pi. So I'm left with rho naught cos beta sine beta over 4 pi epsilon naught times 2 pi here. And then I get this c over omega. And this c over omega comes from this integration here. Because when you actually do the substitution, you're going to get, you know how when we say u equals whatever, then we take the derivative of whatever we have, plug that back in. So when you do the integral, this c over omega should show up. So that's a sort of leftover from the integral. And then what we get is, when we evaluate the limits, we get cos omega t minus a over c minus cos omega t minus b over c. And this is volts. And this is the potential. Any questions? Yes. T minus r over c is it's a definition of how the retarded time it actually is. So whenever you have t equals t prime, in any of these things where you have a time varying source, it takes into account how much time it takes between that actual propagation, right? So we're not assuming it's instant, because it takes some time for the wave to get from point A to B. And so that r over c is another time, right? So that's that time difference. And so we account for the time difference there. If you look at the textbook, it's defined there, that way. So, is all that clear? It's a lot of just bookkeeping, I guess. You have to make sure everything's sort of, do it all step by step. It's not really a difficult question, in my opinion. C. Is that C? Yeah, that's C. Express time domain E in terms of vector and scalar potential. Remember that derivation we did in the first question where we said E equals minus gradient V minus j omega whatever? Essentially we'd just write the time version of that, because that's what it's asking us to do. So we write E of t equals minus the gradient V of t. Well, I guess to be more correct, I should write that this is t, because it is a function of time. And minus partial a of t over v of t. That's all this question is, this part of the question is asking for. Okay? Now it says, ignore a, or the vector potential, find E at the origin. Can anybody tell me what E at the origin is if we ignore A? So if we ignore A, first of all, let's just write what our equation becomes. Our equation ends up becoming just minus V of t, because we've ignored the A term. So if that's our gradient, just by looking at this expression, can you tell me what the answer to that should be? The fact that I'm asking you to do something that looks so complicated in such a simple case, exactly, it's 0. Can you tell me why it's 0? Sorry? The reason it's 0 is because v of t does not depend on space. Therefore, E t at the origin equals 0. What is the gradient? The gradient is just the derivative of the thing in every direction. So you have derivative of it with respect to x in the ax, derivative of the expression with respect to y in the ay, and the same thing in z. This thing doesn't depend on x, y, or z. Therefore, if I take the gradient, it's going to give me 0. You can go ahead and take the gradient, but you can realize right away that it doesn't depend on space. It's fixed. It depends on time only. So you only have a dependence on time. So the thing to take away from that is the gradient is the gradient essentially tells you how this field varies in space. The thing doesn't vary in space. Therefore, it's 0. That's question 2. Any questions about question 2? That's an obvious question. Should have seen that one coming. 24 marks? 24 marks? 25? 24. 24 marks. 4 marks just for drawing the thing. You get marks for setting it up like this. So don't try to skip over these kind of steps. These steps, it seems really redundant, but there's marks earned. All of this is like 1 mark. Like for each step. Field vector, 1 mark. Source vector, 1 mark. R minus R prime, 1 mark. All that's 1 mark. Yeah. Then it depends how wrong. Like, are you going to integrate sine and turn it into like x squared? Or are you going to forget to divide something? If you forget to divide something, you'll probably get the majority of the marks. But the integration itself is worth, 2 marks. The integration itself is only worth 2 marks. So you can do everything right, get the integration wrong, and still get 12 marks. The majority of the marks are earned in setting up the question. Because if you can set up the question, that shows us what you know. If you mess up the integration, that just means you don't know how to integrate. Or your math is weak or whatever. That doesn't mean you don't know what's going on in electromagnetic theory, right? Okay, if no questions about that, then we're going to go on to the third question. The third question is not taken from the same set of problems, because the third question that was actually here is similar to the question I posted yesterday. I posted a question online yesterday. So what I'm probably going to do is just do this again, and then I'll post this again, because it's a relatively simple question. But instead, what I want to do is I want to do a question that's similar to the one we did in the first tutorial. Yeah, in the first tutorial with the boundary, because I remember he told me that, and I know you guys have done reflection, right? At boundaries. So I'm pretty sure that's going to be fair game. So yesterday, yeah, exactly. So if you've done that, then I'm pretty sure that's going to be there. So the type of question where you have a wave or incident on a boundary. So it says that this thing is free space, this thing's a dielectric, find everything. So those kind of questions. So we're going to do. I figured we could do one of those. And what I'll do is this question, the third question that I have from this set that I'm just working off of right now, is pretty much the exact same thing, except it doesn't take into account that boundary. So it's all in free space, or it's all in a certain dielectric. It's not a both type of thing. So it doesn't do reflection coefficient, it doesn't do SWR, and I think that's more likely the type of question you'll see. And not to mention, if you can do the one with the boundary, you should be able to do the one without the boundary anyway. So we have problem 3. Okay, so it tells us we have a uniform TEM wave in free space, which is x less than 0, is normal on a semi-infinite, non-magnetic region. This is x greater than 0. So if I were to draw this, essentially this thing here is free space, this thing here is non-magnetic region, this part here is x equals 0. So in free space, we know I have mu naught, epsilon naught, eta naught. Here I have mu naught because it tells me it's non-magnetic. I have epsilon. I don't know what it is. I can't assume it's epsilon naught because it's not free space. And because I have epsilon, then I must have some generic eta. We'll call eta D for dielectric or whatever. It doesn't say it's a dielectric. No, it just says it's non-magnetic. We'll assume it's a dielectric. It doesn't really matter. We can call it eta D, whatever you want to call it. So it gives us the total E in free space is ES equals 60 pi 2e to the minus j 2 pi x minus e to the j 2 pi x in the AZ direction volts per meter. And now it's just one of those kind of questions where it's like find this, find that, find this, find that. We just go from one part to the next. And it's like part A to L. A. Determine the phase constant. What's the phase constant? Yes. You should know that. You should definitely know that. You don't have to indicate it, but we can. We can call this beta naught. We can call this beta D. It's a good question. You don't have to really draw the diagram. I'm just doing it so we know what's going on. It's nice to organize it that way, so that you can see it. If it says, in this case it doesn't say to draw it. If it says to draw it, then you should. I would draw it either way, because that way you'll actually remember it. Because you might just, when you're in a test, you don't think properly, and you might just go on and say, think that beta in the non-magnetic region is also beta in the free space, which it's not. That's a good point. That's good. Yes, that question. So it says determine the phase constant. What is the phase constant? 2 pi? I heard 2 pi. I'm gonna assume somebody said 2 pi. No, I have to speak louder. Okay, there we go. Radians per meter, don't forget your units. And again, we know that's 2 pi just by comparing with the thing, because we know that in general, ES equals E naught E to the minus J beta X. So that's how we know beta is 2 pi. We literally just look at the thing and we get like 2 marks or something like that. I don't have the mark breakdown for this one, so I'm not going to be able to. I think the whole thing's worth like 35 marks, something stupid like that. Reflection coefficient at interface. Somebody tell me what the reflection coefficient at the interface is and how we find it. You're getting way too complicated. You don't know what ND is, do you? You don't know what ND is, do you? So I can use that equation. You could. It's not going to get you anywhere. How do we define the reflection coefficient? Reflection coefficient. So it's going to be, the reflected coefficient is going to be what? Yes? Exactly. ER over EO. So ER is magnitude, or amplitude, I guess you can say, over EO. So we have this thing here is ERO. This thing here is EIO. Right? So I literally just take ERO divided by EIO and I should get my answer. So I get ERO divided by EIO, which is minus 1 divided by 2, minus 0.5. Your eta D over eta naught definition works, but we don't have eta D right now. So we'll use that later though. I promise we'll use that later. Literally you just look at how much is reflected and how much is incident. How do you know what's reflected, what's incident? You look at these parts right here. Remember in the first tutorial we talked about this. The fact that that's positive means it's traveling backwards, right? E to the minus j is always traveling forward. E to the positive j is always traveling backwards. Yes?
Will it always be that with
No. You have to, that's something. You have to look at the coefficient on the j. Because it's positive j, means it's traveling backwards. Right? I mean, I could flip the equation. And it could be E arrow first. But that's not what we're looking at. We're not looking at the order, we're looking at the exponential. What's on the exponential? If it's minus, it's propagating forward. If it's positive, it's propagating backwards. There's another question somewhere? Yes? Sorry? I'm not sure I understand your question. If I take my paper and I turn it all the way the other way around, it's literally doing the exact same thing. But the thing is, we have to assume that it's telling you it's incident in free space. It's telling you it's incident in free space on the boundary. If it tells you it's incident from the other side, then it could be, sure. It could be traveling in the dielectric and then come into free space. That could totally happen. The entire thing will be defined differently, and that'll be a completely different question. If it tells you the instant wave is traveling first in the dielectric and then goes to free space, like in this case, this is the sort of question that's set up. It says it's a uniform thing in free space is normal on that. So it tells you that in free space and then it goes normal on that one. If it tells you it's in the dielectric and then it's on normal onto free space, then you literally have the opposite of this. So everything that's on this side will go to this side. And your wave will still be traveling this way. We just define the problem differently. So your material parameters will change, but everything else is solved the exact same. Does that make sense? No. It's just the region we're in is just defined differently now. It doesn't do anything any differently. Everything else is the same. All that changes is that instead of having these values here, these values will be different. Your field will still be defined some way. You'll still be able to find everything else normally, and it'll still transmit into the next boundary. All of that stuff is consistent. But what changes is mu will be different, maybe. Epsilon will be different, eta will be different, and then beta will be different. But that's just because of the thing we're in right now. The fact that it reflects or transmits, that happens regardless of wherever you are. So this is the way the problems are defined. It tells you it's in free space, x less than 0, and it's normal on that semi-infinite thing. So you're assuming that it's going from free space into some medium. Okay? And if that's unclear in the way it's written on the test, I would suggest you ask, rather than assume and then assume wrong. Okay? Good questions. Any other questions? Okay, let's go on to two parts. Upside down L is gamma, yes. Everybody else calls it the upside down. So, this is what? And this is what? Mind equals blown, right? I showed this to somebody in, I think, when I was in third year, I showed it to somebody. I'm like, look, they called it the summation sign. This thing is the summation sign, right? It's a bad drawn summation sign. Something like that. I'm getting excited now, that's why. So that's the summation sign, right? But I called it sigma one day. The guy looked at me, sigma? I'm like, yeah, sigma. They're like, no, this is sigma. And I'm like, no, this is also sigma. I'm like, that's capital sigma. They're like, there's capital letters? That was the end of the conversation. So it asked us for the... literally, yeah? That's all Greek to you. Characteristic impedance in free space. So this is asking for eta. Yeah, that would be definitely useful, eh? But I guess you learn them as you go along. But some people just don't know what letters are. Like even some professors just mispronounce letters all the time. And they'll think one letter is another letter when it's actually, and it drives me nuts. I just try to ignore it. So this is mu naught over epsilon naught. If you don't know what this value is off the top of your head, You can calculate it by approximating these. You're not allowed using a calculator on the test, just so you know. Yes? Yes. When do you know to use epsilon E? Epsilon E, if you look at the definition, is defined with a conductivity. Has a sigma in it. If you're in a conductor, you will need to use that. Chances are you won't be in a conductor because that makes the problem overly complicated. But when you have epsilon equals epsilon E, which is like epsilon times 1 plus sigma over j omega epsilon, something like that, that only exists when you have this sigma, which is only in conductors. Because if you're in a dielectric, the conductivity is not good. So you can approximate this whole term to be 0. So that's only when you're in a conductor, when it gives you a sigma. If it tells you conductivity is this, then you know that you have an epsilon E. If it tells you non-magnetic whatever region, don't worry about conductivity. Because chances are, I mentioned this in the last tutorial, I think, chances are if it's magnetic, it'll also be conductive. Because most materials that we know to be conductive are also magnetic. Things like copper, things like aluminum. Chances are. So if it says non-magnetic, no sigma. Just it's epsilon equals epsilon naught times epsilon r. Like we deal with typically. Like we're going to see in this case here. So this is just eta naught, which is a free space. If you don't know, it's 120 pi. Is that given it's given in most tests actually. It's given as an important constant. So I guess you're lucky. This is units of ohms. So characteristic impedance of free space is 120 pi. And this is a well-known constant, and it's given in most tests, I should say. Part D. And this is the characteristic impedance of the dielectric. Now I'm calling it a dielectric. The question doesn't tell me it's a dielectric, but I'm assuming it is because it has dielectric-like properties. It's non-magnetic, and it tells me that it's linear, loss-free, and all that type of nonsense. You can call it just region 2 if you want. I'm just calling it a dielectric because it's dielectric. I guess we should call it region 2, so I don't want people coming to me after and saying, but you said it was a dielectric. It wasn't a dielectric, right? So we'll call this region 2. And I'll call this region 2 up here. Okay, so that deals with that. So here's where we need to use that eta d, or gamma equals eta d minus eta naught over whatever. So we'll say gamma is, we'll say eta 2 because it's in region 2 minus eta naught over eta 2 plus eta naught. Now if you solve this and rearrange it, which I'm not going to do because it's just a mathematical exercise, you'll find that eta 2 is 40 pi ohms. Okay, part E asks for SWR in free space. How do we find the SWR? SWR, there's this equation, we call it S, so it's 1 plus the absolute value of gamma over 1 minus the absolute value of gamma. Remember, gamma was minus 0.5. Gamma equals minus 0.5. So this thing becomes 1.5 divided by 0.5. And then so S is 3, if I'm not mistaken. And S is dimensionless because it's a ratio. Part F asks for SWR in region 2. Can anybody tell me, well I should call this S1 then I guess. And S2. Can anybody tell me what SWR is in region 2? 1. Why is it 1? Exactly. Another way to look at it is there's no reflection. It's a semi-infinite region. X greater than 0 goes on forever. The wave will never come back. Therefore, it will never reflect. Right? If region 2 is infinite, you'll have no reflection. And it tells you it's a semi-infinite region. It's part of the question. G. Oh. Well, I think I know why no one's showing up now. It's because I'm posting the videos on YouTube. I'm doing too much work for you guys. That's what it is. That's why no one's showing. I'm wondering, where's everybody? It looks like more people to show up. I'm sorry? Okay. I mean, I always prefer to be there in person. You can always ask questions. It seems a lot more interactive. I mean, people at home are going to be sitting there like, why does this happen? Why does that happen? So, you know. So it asks you to find HS in free space. So there's two approaches. You can either use Maxwell's equations and find the curl and all that stuff that I did in the first tutorial, I think. Or you can use those little equations if you want to memorize them. I'm going to use those equations just because I guess I can. What I suggest you use these, whichever one's easier for you. If you can memorize this, if you can memorize these equations, no problem, go for it. If you want to use, you haven't seen that equation before? No? No? If you remember any equation, I think it would be these ones you should remember. These are, I mean, it makes it easier. You can still use Amperes Law or Faraday's Law and still solve them. So it doesn't take that long. I mean, if it depends on how fast you are. I mean, maybe it takes an extra 30 seconds, but it saves you from having to remember anything, which I hate memorizing things. So I always like to just know a little. I know a few things, and I'll just go from there. But hey, whatever works for you. So HSI, AP is the unit direct vector in the direction of propagation. So in the case of the incident wave, it's what? It's the positive x-axis, right? If you look at here, the wave's going to be going this way, positive x, right? So for the incident, because if it's going the other way in my head, there's no point in me doing the question. If the incident wave is traveling in the opposite direction, go home. There's no question. Right? Because it's not doing anything. If the reflected wave is going in the opposite direction, that's a different story. This is the incident wave. So AP is going to be AX cross ESI. ESI is what? 120 pi e to the minus j2 pi x. And this whole thing is divided by eta naught, which is 120 pi. And this thing is in what? AZ, right? Sorry? 60 times 2. It's factored out, right? If you look at it, it's factored out. Here. There's a 2 there. That 60 pi is factored out. This is incident. For the reflected, it will be 60 pi. So x cross z gives me minus AY, right? So these two cancel. I get minus e to the minus j2 pi x AY amps per meter. And this is HSI. Okay, that's one part of the question. Now I need to find x cross y, or x cross z, sorry. Right? Right hand rule. HSR, so the reflected, in this case, I have the direction of propagation for this reflected wave is what? Minus AX. It's reflected. Reflected waves going in the opposite direction. It has to be. Right? So, cool. So I get minus AX cross, this thing is minus, what? Minus 60, right? Minus 60 pi e to the j2 pi x. If you're confused about the direction of propagation, just look at this thing here. Positive j tells you it's going negative, right? So if you do get confused, you should be able to reason with what's in front of you and to be able to solve that. Now this is 60 divided by 120 pi, because again I'm using this equation here. Should get rid of that probably. I don't want to think it's a conjugate. Oh, not orange. And so this is in the AZ direction. So minus, these minus signs will end up actually canceling. And this is AZ. And so what I end up getting for the reflected wave, sorry? What? How come it's minus? That's the way it's defined. Yeah. The reflected wave doesn't always have to have a negative amplitude though. So this number out here doesn't always have to be negative. That comes with the fact that our reflection coefficient is negative. Because our reflection coefficient can be positive too. If it's negative, it means it has a phase on it. Right? I should hope. Then again, we have this x cross z. Right? And so if I have x cross z, again, I have minus. So I have this minus 0.5 e to the j 2 pi x a y amps per meter. Then my total magnetic field is just going to be minus e to the minus j 2 pi x. This is my forward traveling wave. Plus 0.5 e to the j 2 pi x, which is my backward traveling wave, and then I have AY, and this is amps per meter. And that's our total HS in free space. Okay? Okay. Any questions about that? There is one for going the other way. So for going from this is for going from H to E. If I want to go from E to H, the equation goes the opposite direction. So the cross product is actually it's HS times eta naught cross AP. What I'll do is I'll make a video and I'll post all that on. Okay, I'll make a note of that. Video for shortcuts. Because everybody's lazy, right? Nobody wants to do any work. So now it asks ES in region 2. So how do we find ES in region 2? So first let's write ES I, because we're going to need this. ESI is 120 pi e to the minus j 2 pi x pz. Correct? Correct. So this is incident. So this is in region, or no, I should say in free space. So this is in free space. Now it's asking how much of it is what's the transmitted wave is essentially what it's asking. So it wants to find what's in region 2. So we have to start by finding the transmission coefficient, tau. If you recall, tau equals 1 plus gamma, which is 1 minus 0.5, which is 0.5. So therefore, the amplitude of the transmitted wave, let's just say EST, will be something like this then. So it'll be 120 pi times 0.5 e to the minus j beta 2, let's call it, x. AZ, that doesn't change, and this will be volts per meter. Now we need to find beta 2. Because if I don't have beta 2, I don't have a full equation. So now the question comes down to finding beta 2. Now, we did this in the last tutorial, I believe. So we know that beta 2 is going to be omega mu epsilon. You remember this equation? I would hope you do. This is omega. This is going to be square root mu naught epsilon naught epsilon r. And this thing here is actually called beta naught because it's in free space, right? So that means I can replace this as beta naught square root of epsilon r. This is beta 2. Now we have to find square root of epsilon r. So let's bring this up here and say find square root of epsilon r. How how do we do this? If you recall, eta 2 is this, right? Mu naught is because it's non-magnetic. Epsilon because it's non-magnetic. So this becomes mu naught over epsilon naught epsilon r. This becomes mu naught over epsilon naught times 1 over square root epsilon r. If you recall, this thing is eta naught. It's a terribly drawn eta. Eta naught, that's even worse. So hard to draw sometimes. Yeah, I'll take that. So now, eta 2 is going to be eta naught divided by square root epsilon r. So, I get square root epsilon r equals eta naught over eta 2. Eta naught was 120 pi. Eta 2 is 40 pi. Therefore, square root epsilon r is 120 pi divided by 40 pi. We already found eta 2, if you recall, is going to be 3. So now I know beta 2 is just beta naught times 3. So beta naught times 3. What was beta naught? 2 pi. 2 pi times 3. Beta 2 equals 6 pi radians per meter. And that is, well, that shouldn't be purple, it's not the final. Let's give that an orange one, just to know it's intermediate. So now what I can do is plug beta 2 into EST, and then that gives me EST was 60, right? Yeah. 60 pi e to the minus j 6 pi x a z volts per meter. Now we can get the purple volts. Any questions about that one? I know that was a little more involved compared to most of the parts. Part I asks us for HS in region 2. I know a lot of people will probably be tempted to use the transmission coefficient and multiply it by the incident magnetic field. That's incorrect. We don't define the transmission coefficient in terms of E. We define it in terms of H. We define it in terms of E. So tau is actually ET divided by EI, not H. And there's a difference. So make sure you don't forget that, and make sure you don't do that on the test, because that's wrong. It gives you an incorrect expression. So now that I have EST, I can say HST, and I can use this equation, this little shortcut equation that I have here, and this is eta 2. Just a note on this equation here, there have been times where he has asked, or the question has been asked, to determine H or E or whatever, one or the other, without using Maxwell's equation. And if you don't use Maxwell's equations, you have to use this equation, which is silly if you ask me, and I will say that over and over again, just because if you can't have a course on electromagnetic theory and ask not to use Maxwell's equation. In the case that it asks you not to use Maxwell's equations, you have to use this approach. So I guess this equation and the one that goes from E to H, which I will make a video about, I guess these are worth the while to actually remember. So AP is AX because it's propagating the positive, because it's transmitted, so it must be propagating in the same direction. EST is 60 pi, e to the minus j 6 pi x, and this is in AZ. This is divided by 40 pi because this is eta 2. So again, x cross z gives us minus ay. 60 pi divided by 40 pi is 1.5, so that's minus 1.5. e to the minus j 6 pi x a y amps per meter. This is HST. So this is our transmitted magnetic field, or the magnetic field in region 2. Any questions about that? Okay, so this part asks us for the time average, I'm not going to write pointing vector, let's write P, of incident waves. I don't know which P this one is. I know there's like 7 different P's that he uses in the course. I don't know. I'm just going to call it P average. I guess you can figure out the details. So this is, we define as 1/2 real of ESI cross HSI conjugate. And this is going to be 1/2 real of 120 pi e to the minus j 2 pi x. Remember, we're in free space here because it asks for the incident waves. This is an AZ. I'm taking the cross product with minus e to the minus j 2 pi x a y. But this whole thing, you have to keep in mind, has to be conjugate. So I end up with 1/2 real 120 pi e to the minus j 2 pi x AZ. Well, I'll leave that for after it is AZ cross minus e to the positive j 2 pi x, because I took the conjugate there. And if you remember, when we take conjugates, we flip all the signs on the j terms. And so I have 120 pi, well, what we first realize is that these terms just cancel. And so this becomes minus 1. So then you have z cross y, or z cross minus y, and 120 pi times that divided by 2. So I have 120 pi here. Z cross y minus y is going to give me 8x, and this is 60 pi. Now, how do I know if I did this correctly? There are some ways to figure out. Can anybody tell me some characteristics of this time average pointing vector that are always consistent? Exactly. The first thing to realize, and I missed a sign here, sorry. First thing to realize, it should be in the same direction as propagation. Our incident waves are traveling in AX, positive AX I should say, and our time average pointing vector is also traveling in the same direction as the incident waves. The second thing to realize, it's time average, it's entirely real, because we take the real part of it. If I have J's somewhere in here, it means I've done something wrong. So those are the two real main things to figure out. If you have like some term dependent on J, or some term depending on space, or some, well, maybe space you might have if your amplitudes are like that. But you should never have a J. You should have no imaginary parts. That should be entirely real. And that's just because you're this thing here. It says real, so you want to take the real component. If you're taking the whole thing out, you're doing something wrong. So I guess the easiest way to tell your propagation direction is probably the easiest sign to see. And then beyond that, you can figure out if everything is real. And you're good. Yes. Conjugates. One's conjugate of the other. Multiply them together. Multiply that. E to the minus j 2 pi x times e to the positive j 2 pi x. Cancels, right? So the way the thing is defined is we take the conjugate. You take the conjugate because if you don't take the conjugate, you are left with something imaginary. If I were to just multiply that straight, I would end up getting e to the minus j 4 pi x. That's not what I want. I want it to be real. I want it to be entirely real. I want it to get rid of all the imaginary parts. You don't necessarily get rid of the j's, you take the conjugate. We take the conjugate to get rid of the j. But you don't just get rid of the j off the bat. You have to take the conjugate. So it might be that you have a j in the front. So instead of just minus 1 here, like this, what if this is 1 plus j? And if I have to take the conjugate of the whole magnetic field, then this thing would become 1 minus j. Right? So you have to remember that you take the conjugate. And then, but when I take the real part of the whole thing, that j term would disappear because I'm only taking the real part. But you have to remember it's conjugating, it's not just making everything disappear. So you have to do the step with the conjugate, because again, these are simple cases, but you might see something a little more complicated, I don't know. I mean, I'm not writing the test, right? I can't. I can only, you know, I know nothing about what he's doing in the course. And that's been the disclaimer since the beginning, right? You know, even this that I'm doing is not part of this is not part of the job description. This is no, I don't. I don't get paid for this.
What are you doing?
Because I know how much people complain about this course, and I remember how much people complained when I did the course, and I remember a lot of people not knowing what they're doing, and so I'm just trying to help you guys out. I guess we can appreciate it after. So we have 2 parts left to finish this. We only have 10 minutes left. We can hold hands around the campfire later. You'll never see me in a bar. There's no time for that, man. Come on. Talking about bars, man. Come on. So now he wants us to find the same thing in the with the transmitted waves. And again, we take the conjugate. And so I have 1/2 real. This is 60 pi e to the minus j pi. Sorry, j6 pi x az. Sorry, az cross minus 1.5 e to the j6 pi x ay. I'm not going to go through the entire multiplication. Oh, but this whole thing is conjugated. Remember that. This thing is conjugated. Sorry, this is minus. This should be minus. That's just drawn together. That should be minus j. Now I have 2 dots. Minus j. There we go. So when I conjugate that, I should have the 2 canceling each other, and what I'm left with is 45 pi ax watts per meter squared, and this is PAV subscript T for transmitted. And I'll give this subscript I for incident. JKL. Now it asks the percent. Oh, let's be consistent. Let's keep it green. Percent of incident power transmitted to region 2. Can anybody tell me what that is? Knowing very well that this is the time average here. 75% is correct. So, percent transmitted, I guess we can call it. There's really no equation for this. It's literally just dividing. So I take 45 pi divided by 60 pi, get 0.75. 75% transmitted. Okay. That is the last part of the question. How many marks is that worth? I don't know. I would say something like at least 30 marks for it. And I mean, it's relatively simple steps, I guess. It's not overly complicated. Any questions about this? Yes? Take the reflection coefficient and subtract it by? No. The way the power is related to the transmission coefficient is by a square relationship. So what you do is take the square of the reflection coefficient and then subtract that from 1. Then you'll get 0.75. So the way the powers are related by reflection coefficient is with a square relationship. So the amount of power transmitted is going to be 1 minus gamma squared. Okay? Any questions? This is what's given. It's a uniform TEM wave in free space is normal on a semi-infinite non-magnetic region. That's it. If it is magnetic, all that changes is mu r. Mu is mu r. It won't be mu naught anymore. Non-magnetic means mu equals mu naught. Magnetic means mu equals mu r times mu naught. So you have that relative multiplication thing. We'll talk about it after.